time to get started. I see everyone but Christy and Denford here. Did you guys bring your clickers? I am going to ask a number of clicker questions as we go through here. Today's lab is about graphing motion. Graphing motion is something we do a lot in physics because it helps us to understand things in an easy to see fashion. So we're going to go through first some introduction to graphing, and then you're going to do some experiments that probably could have done without any of this lecture to help you understand the information you can see from a graph and to be able to relate motion that you understand to seeing that motion on a graph. So I'm going to start off here with just this information here. I have a car that has been measured to have these positions at those specific times. Now, if you look at that data for the car, what can you say about the motion of the car? Just looking at the data.
It gets faster up to 20 seconds, and it's kind of starts getting slower acceleration, but for other reasons.
You say sec? Okay, well, let's make the graph and try to understand this better. Now, it stops, that's right. I had actually prepared and had a graph all set up before, but yeah, it's not there anymore. So I'm going to copy my date. That's not the way you do it. I'm going to copy the data down below so I can view the data when as I make my graph. Okay, that's a little technicality. Basically, I screwed up. Try number 3 will be full of success. See that? Full of success. So I'm going to graph this data. Now, when you make your graphs, something that's important that you do is that you are careful with things like the scale. Make sure you go, each block is the same amount and use straight lines and stuff. So I have a straight line tool here, and I'm going to make my vertical axis like, and my horizontal axis like, and get some labels on there. So when you're making the graph, you need to label what's on each axis so when anyone looks at it, they know what it is. So you probably don't know which one should go on which axis. As a basic rule, if you have time is going to always be on the horizontal axis. And notice I didn't just put time, I also put the units I'm going to have it in. And now I'm going to put the numbers. I probably should have put those a little lower so I'd have room for the numbers above them. So my minimum time is 0, so I'm going to start at 0 here. My maximum time is 35 seconds, so I'm going to say, how can I space this out to make it reasonable going up to 35 seconds? Now 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, I'm going to go 2 blocks for 5. So there I have my time spread out on the horizontal axis. Now for the vertical axis, what's going to be plotted on the vertical axis? Position. So I'm going to label this with position. What are the units for my values? Centimeters. And then I need to go up to 18. So I think I can go by ones. Okay, the top one is 8. Well, let's go up to... So there I have my two axes labeled. A title for the graph. When you make a title for your graph, the title should always explain what's important about the graph or why someone would be looking at this graph. So, what are we going to be making this graph to do?
Position of the car and time.
Okay, so I'm going to put motion of car. That gives me an idea, okay, this is what the graph's about. It's about the motion of the car. A lot of people learn things like, oh, time versus position. Well, you can see time versus position just by looking at the, if it's properly labeled, you can see it by looking at your axes. Making a title time versus position doesn't help anyone. It's just a waste of your time writing. Your title should be something that tells you why you're looking at it. Now we put the data on. So we need to be careful in putting that data on. I'm going to change color and change it back to layer 2. So my first data point was here at 0, 0. My second data point over 5 up 4.1, so up there. 10, 7.9. 15 and 12.1. 20 and 16. 25, 30, and then we go up to 18 for the last one. So now if you look at this, you see this motion appears to be 3 straight line segments. So I am going to draw straight lines for this motion. There's my first line. There's my second line. There's my third line. Okay, so now I've graphed it. We've gone through the mechanics of making the graph. But just making the graph doesn't mean we understand it any better. Right? We need to look at what this means. So just like with what we did in class today, I'm going to... Oh yes, that's what I wanted to change. Take off the line tool. I'm going to take this and say, well, I have straight lines, and I'm going to find the slope of the straight line. So for instance, this one here, let's just find the slope. So my rise here is going from 2 to 14. So 14 centimeters minus 2 centimeters, that's my rise, which, of course, that's 12 centimeters. And my run is 17.5 seconds minus 2.5 seconds equals 15 seconds. So now if I take this and I find the slope, what is the slope of that line? Okay, 12 centimeters divided by 15 centimeters. 12 is 4 times 3. 15 is 5 times 3. And so that's where he got the 4 over 5. 4 over 5 is 0.8. And that's not 15 centimeters, that's seconds. So that's equal to 0.8 centimeters per second. What kind of unit is a centimeter per second? It's a velocity or speed. And in fact, if you look at this, rise over run was change in what variable? What was the rise? Change in position. Divided by the run was change in time. So the speed was equal to the slope because it's change in position over change in time. So I can look at that slope and say, aha, this is how fast it was traveling. So now when we look at the graph, look at the numbers, it wasn't clear to me. But looking at the graph, I can say, okay, it was traveling at a constant speed for the first 20 seconds. And that speed was 0.8 centimeters per second. What was it doing for the next 10 seconds? It was stopped. How do you know it stopped?
In the same position.
It's in the same position. Very obvious. Looking at the graph, if it's a horizontal line, that means same position, so it's stopped. So horizontal line here means it's stopped. Then what does it do for the last 5 seconds? It moves. Is it going faster or slower than it was initially? Oh, we got differences of opinion.
Well, yeah, it's going 1 now.
What is your key for determining how fast it's going? The slope. So this goes up to, and the rise over run is going over 5 seconds for the run, going up 2 centimeters. So this one has a slope of 2 centimeters per 5 seconds, which is 1/2 the speed of the first one. So it's going slower. If it was going backward, what would the graph look like? It would have been sloping downward. A line like this would be going backward. And positive slopes going forward and negative slopes going backward. Does that make sense? Yes, Michaela.
How did you decide where to start your rise line?
How did I decide? Okay, when you're graphing data, usually your data does not all fall in a perfect line. In fact, most of the time, your best fit line, that is the line that goes the closest to all of your data points, never touches a single data point. Right? When you draw the line, you're not connecting dots. You're not connecting first and the last or anything else. You're just drawing the line that's as close as possible to all of them. And so since usually your data points aren't even on the line, I choose specifically points that aren't data points. I want them to be as far apart from each other as possible, because if they're far apart, my uncertainty in how close I am to identifying what the value was at the points I use is small compared to how big the range is. So I want them as far away from each other as possible. So I chose one that was fairly easy to read that was close to the bottom end, and one that was fairly easy to read that was close to the top end. In fact, I chose the points that were as far away as possible and not being data points and easy to read. And that's basically what you should always do. Choose the ones as far apart as possible that are easy to read and not data points. Any other questions here? Okay, important things we had here. If it's faster, what does that mean? Steeper slope. If it is forward, how do we determine if it's forward? Positive slope. And backward, of course, is negative slope. Come on. So here's a graph of some data. Can you describe what's going on in this graph? It doesn't have a title, but let's assume that we're analyzing the motion of a cart again. When is it going backward? Okay, this is what Rachel said. It's going backward after 50 seconds. It's going backward here because the slope is negative. So this is backward. This part here, what is it doing? Andrew? Stopped. And what's it doing in these two parts? Well, that's actually the data that we plotted up to here. That is exactly what we had. It's just extended for more data on it. And I've already gone through this. There's no point in asking those questions now. Instead, let's go to some more clicker. Whoa, I got to change the app here. Okay, now you can answer the question. The graph shows the position of a car with respect to time. Does the car ever go backward? Does anybody know how to get a hold of Denford? He may have forgotten that we have lab. Nope. Do you not have your clicker, Christy?
Mm-hmm.
Do you not have your clicker?
Oh, I do. It might be like, because the roads are kind of bad. So
That's true.
it might be that. So when I was driving here, it was really scary.
Go play bumper cars tonight. Yeah, we're all going to Chipotle tonight to support, what is it, College View Academy?
Yeah.
All right, there we go. So what we have is 0171. 7 people said it's going backward during the third not labeled segment. And those 7 people are correct. They're correct because during that segment, what is it doing that tells you it's going backward? It has a negative slope. It's sloping downward instead of sloping upward.
Quick question, how would you graph it doing a U-turn?
How would I graph it doing a U-turn? Okay, we're doing one-dimensional motion, so we're just going forward and backward. And so it would just be going from like this to like that. Okay, is the instantaneous velocity. The instantaneous velocity means the slope at a single point. Greater or less than at A compared to B. So which one is higher speed, here or here? Just to make sure it's clear, this means A is faster. This means A is slower. Okay, everybody has answered. Oh, crud. I pressed the wrong button. Woe is me, for I am undone. Everyone's answered, but for some reason the answers are off the screen and I cannot read them. It's showing them, but it's showing them over here. So I can't see. I will assume you all answered correctly. You did, right? Which one's going faster? A, because it's steeper. Oh, hey, now it shows. That's weird. So yes, all but one person said that. Really weird. Okay, so now looking at a graph of, what's different on this graph? It has time here, but over there it's velocity. So we're looking at velocity versus time instead of position versus time. So of course that means it's going to be a different thing we're reading. So when we look at this, we can see that, hey, it was going at a constant velocity up until here. And then from there to there, actually, from there to here, the velocity did what? It decreased really rapidly. What do we call it when the velocity changes? An acceleration. So we had an acceleration. Is that a positive or a negative acceleration? Negative, because it went down. So here it was zero acceleration because it was constant velocity. Then we had negative acceleration, zero velocity. Positive acceleration, zero velocity. Negative acceleration, what's it doing right here? It's going backward. So we can read this and, it starts to make sense. You can see the motion in your head, so to speak, by looking at the graph. That's why we love graphs in physics, because you can see how the data is working by looking at the graph. And of course, we've already done finding the slope of the graph. So in the graph shown, is the velocity constant for any time? And you're supposed to, of course, answer which time period if your answer is yes. Dagger to the heart. Eight people said it's constant velocity from 0 to 2, and one said from 2 to 4. Now, if you look at this graph, looking at what we did before, these are all straight line segments. If it was position versus time, they would have all been constant velocity. But this is not position versus time, it's velocity versus time. So the velocity was constant only from 0 to 2, which is what almost all of you said. Then from 2 to 4 seconds, the velocity increased, so it was sped up. Sped up, what do we call that again? Acceleration. So it's accelerating forward. It's a straight line, so the acceleration was constant. Then at 4 seconds, what's it start doing? It's accelerating negatively, slowing down, at once again a constant rate for the entire time. So we can look at this velocity versus time, and we can get the information about the acceleration. Now, this isn't limited to information about acceleration, because we know that the change in position is the velocity multiplied by the change in time. So, for instance, going from here to here, the time was 2 seconds and the velocity was whatever this number is. If I multiply this number by the 2 seconds, it'll tell me how far it traveled, right? Well, geometrically, I almost said geographically, multiplying these two numbers is finding the area of this box. And it turns out mathematically that's correct. The area underneath this tells me the distance it traveled. So if I want to find the distance it traveled from 2 to 4 seconds, I would break it up and find the area in both of those two segments, the total area under that line, and that would tell me the distance it traveled in that time period. So a graph of the velocity versus time tells you about acceleration by looking at the slope. It tells you about the distance that's been traveled by looking at the area under the graph. I'm getting tired of these clicker questions too. People want to know the truth. In the graph shown, during which time interval is the acceleration the greatest? Okay, once again it was 8-1. And this was the correct answer. This is a steeper slope than this. How do I know? Because it goes from here to here in 2 seconds, and then coming back down, it hasn't even reached this level again after 4 seconds. So this is steeper than that one. This has the biggest acceleration, and this is a positive acceleration. This is a negative acceleration. I hope I'm about... I feel like just going to the end. We had the question. A car moves along a straight line, straight road. Does it ever go backward? Assume no U-turn. So we're assuming that it doesn't go and turn around like this, because in one-dimensional motion, going backward is the U-turn. Okay, this one here wasn't so clear to people. What is the velocity if it's going backward? Negative. Where was that velocity below the line? Simple answer? It wasn't. Right, it was accelerating to the rear here, but it was still going forward because this is still, the velocity is above 0. So it's accelerating to the rear, slowing down, but it's still moving forward.
Okay, so it doesn't go backward until it gets below the black line?
That's right.
Okay.
So if it went like this, then it would have been going backward in this portion here. Sorry. I draw it and stand right in front of you. Perfect. That's teaching at its best right there. Nobody laughed. Okay. During which time interval, remember this is velocity versus time again, during which time interval did it travel the greatest distance? Okay, our answers were not very comforting. Here's a good one to talk to the people around you about how you determine the distance that it travels.
I figured it out as I was looking. I just substitute velocity or distance. Words, but
Okay, let's answer again. We've had some good discussion. Okay, so it's open for answering again. Zach, you want to put your answer again? Okay, this time we had 2700. The correct answer was from 2 to 4. I heard some good ideas. What I had said previously was the area under the curve tells you the distance. And so you look at the area in the triangle with A, the area in the rectangle with B, and the area in the trapezoid, or whatever we call that shape, rhombohedron, I don't know. With C, it's reasonably clear that this one here has the biggest area. But then I heard other people thinking it through logically. They're all the same time. And if they're all the same time, since distance is the speed multiplied by the time, the one with the highest speed is going to be the one that goes the biggest distance. That is perfectly good logic, and it gives you the same answer because it's the highest speed. The average speed in B is higher than the average speed in A or C. So either one of those is perfectly good logic. Perfect reasoning to get the answer right. Now, changing to acceleration versus time. What could you tell me is going on from here to here? That's all you can tell me. All you can say is constant speed. That speed could be 0, could be 100 miles an hour. I don't know. Don't have that kind of information here. I just know it's constant speed. What happens at 20 seconds? It slows down. Person must have braked really hard, or if they were in reverse, slammed on the accelerator. And then it goes forward at 30 seconds. What do? They accelerate forward, and so on. So you can read this. This is actually the acceleration graph to go with it's the same graph we've been looking at all along. Where is it? I know it's here. There we go. It's the acceleration graph that goes with this here. And this here is the velocity graph that goes with the one I plotted by hand, except for it goes out for more time because remember we ended right here. I think I went one further, but that's okay. This here is actual data. I went out and plotted the data for what people are doing in the 100-meter race. This was the 2009 Berlin World Championship. Because a lot of times when we see sprinters running a race, like Usain Bolt, we're like, man, that dude is just fast and he's running away from everyone. He must be going faster and faster. What actually happens, the left picture is what we project goes on in a 100-meter race. For the first about 30 meters, or as it shows there, about 3 seconds, they're speeding up to hit full speed. Most human beings, as soon as they hit full speed, they start slowing down. But not all of them. So if you look here, you'll see that, and I'll zoom in on the data. Pretty proud of myself for, going through and plotting all of these sprinters. You can see that here's the loser. He was slower here, and he got tired and really slowed down. But they actually all pretty much were speeding up through 70 meters. So they pretty much got close to top speed after 3 seconds in about 30 meters. And then they were maintaining and speeding up just a little bit. And then that guy who lost, he slowed down a lot. What did the winner do? He slowed down a little. They all slowed down. No human has the stamina to go full speed for 100 meters, it turns out. But the one who won, well, he pretty much was ahead the whole way. He was the fastest start, the fastest top speed, the least dropping overall. So to me, it's interesting looking at these graphs, thinking about what those guys are doing. And of course, it's more interesting than looking at the general physics version, the idealized, they speed up and then they run at constant speed. But if you were looking at this race, if you were comparing this guy to this guy, what would you think was happening just watching the race? Football announcers would say, "Ooh, he just hit another gear," right? They would suggest, and you would tend to think that this guy put it in the afterburner, he's really going now. When in fact, now he's slowing down just a little, but that guy's slowing down a lot more, so it makes it look like he's sped up because, well, they're all going super fast. If I was in this race, there would be a line like this. Well, I wouldn't be down to negatives. I'd walk it out, I just want to make sure everybody realizes these guys are, a lot more amazing than me at my best, that's for sure. I'm not a sprinter. You can tell I got the build for a sprinter, but... Okay, let's go past this and get to the actual lab, because I think we've already seen enough. We want to get to doing the lab. Come on. I know it's one of these. Okay, so here's the actual lab instructions. Oh, I've got your lab book still, don't I?
Yeah.
I graded them like the day after the lab, and I never gave them back. Let me get those now. I am totally sorry. I graded them right away. I was very proud of myself. Now I'm not as proud. Okay. I guess nobody prepared for today's lab, did you? You could have told me you haven't given us back the lab guides yet. What we're going to be doing is making graphs of ourselves moving to analyze it. So if you look in the lab guide, you've got a nice page here of introductory material. Look how quickly I went through that. Here's our instructions. The first thing you're going to do is make a graph of your motion, the position as a function of time. And the first time you go through, you're just going to sketch and describe the motion here. So I have 4 types of motion: slow walk away, fast. Fast means faster. Don't be running. We want everybody to be safe, right? So let's have Tyler be my helper here. I have, if you in the cupboards next to you, you have all of this equipment. So we have this motion sensor. On the top, it has a little button. You can flip back and forth between a stick man and a little cart. Tyler's a stick man. So I got on the stick man, and I want you to stay in front of it. So I'm going to change over so you can see the software, what it's going to look like. Why don't you just walk facing this way and walk backward, and then you can see what's going on as well. So right now what you see is not it. Okay, everything's set up here. I'm in the first tab. Notice there's 3 tabs here. We're actually not using the 3rd tab. In the first tab, and when I hit record, that thing's going to start ticking. Now what it's doing is sending out an inaudible chirp. The tick you hear is it turning on and off. An inaudible chirp, it comes, it bounces off your body, reflects back, and it has a microphone, measures the time from when it emitted the sound to when it came back, and calculates the distance away. So you move away. Okay, so it made this nice graph. So now I'm going to put in here a picture of what it looked like. Now this needs to be qualitative, not quantitative. What does that mean? It means it doesn't have to be accurate. It has to show the rough shape. And so I'm going to say, okay, I'm going to just cut off this part, say, well, that was before he got going. And that's what I'm going to put. So it goes something like this. Right? And then I need to have a description. Notice here it says, be sure to include a description of the motion with the graph. Well, where are you going to put that description? Just put it right here. How would you describe that? How would you describe this graph? Well, just describe the line. Not going as deep as you're going. What I hear over here? Okay, a positive slope. And is it a straight line or a curve? Straight. Now that was slow walking away. Now let's try slow walking toward us. So let's just repeat. Okay, so I have that one. So I put that here and I describe it. Then we've got moderately fast walking away and moderately fast walking toward. Now you notice I have both of these on the same graph. I want to keep them on the same graph so I can actually compare. I have these first 2 drawn. I want my next ones to be things I can compare to them. So I can tell if it's steep or flat or etc. One thing that's good to know, this has a little auto fit. This button here made it so it filled the screen. When you're making graphs, you want to fill the screen with your graph, and that did it automatically. I can also do things like this to scale it manually. That hand allows me to shift where the axis is. You saw me do that earlier. So you've got a lot of controls. I can delete data here. Clicking right there will delete the last run, or I can delete all of them, or delete just the first one. So I can take control, get rid of, if I do one, I'm like, ugh, we totally screwed up, totally walked out of, if you walk out of the path that this thing is pointing, well, come walk in front of it so they can see what happens when you walk out of the path. So go off to the side. Pretty clear something went wrong there, right? So I would say, well, let's get rid of that last one. That was just flawed. So you can manipulate the data that way. So you're going to go through and do these 4, making sure you have descriptions for each one, and draw the shape. Then you have 2 questions. Describe the difference between graphs made walking slowly versus quickly. Now, we went over that in my little lecture, but you're going to do the experiment so you can look at your data, see if it actually does what I said when I was describing things. Likewise, what's the difference between walking forward and walking backward? Now, when you do these, you're going to be working in groups of 2. Because Denford's not here, I will be the partner for the odd person, because it's easier to have 2 people than 1 or 3. I want one person to do a forward slow and a backward fast. The other person to do a forward slow, or a forward fast and a backward slow. So each person does a fast and a slow, and also a forward and a back. Make sure you answer those questions. Now that you've had some experience, we're going to come and using a dash line sketch what I think will happen if a person starts 1 meter away from the detector, walks slowly away for 3 seconds, then stops for 3 seconds, red for stop, and then finally approaches the detector, green for go, for 3 seconds. Now I'm going to do that. I'm going to do something that's clearly wrong, okay? Just because I don't want people copying me. Question?
Are you sketching on the lab because it's not up there?
All this. Wow. So you haven't seen any of my sketches.
Sure haven't.
Nobody thought to say, hey, why aren't you... Where are you going to put your descriptions? Like there. Thank you, Michaela. I'm so embarrassed. Okay, so you put your answers in here. You're going to use a dashed line for your predictions. So my prediction, like I said, my prediction is wildly wrong. Okay, there's my prediction. Make sure you do a prediction before you move on. Don't say, well, I'm just going to do it and then I'll make my prediction look like the actual. That doesn't really help you. The prediction is to see if you can internally predict what's going to happen. Well, then you go ahead and do the motion. So you start there 1 meter away. It doesn't have to be exactly 1 meter, but, about a meter away. Walk backward slowly for 3 seconds. Stop for 3 seconds. Walk forward slowly for 3 seconds. Your partner can tell you, stop, go, right? Each person needs to do their best effort. So that means if we have Rachel and Colby are partners, Rachel will do her best job, and then Colby will do his best. Now it says here, print it. Print your best effort. How you print is a little bit interesting. Let's say that I want to print this graph. First, I want to make it fit the entire screen. So I just use the fit button. That's usually the best. What was that? I have to flip it again. Thank you for keeping me straight. All right. So it was all odd size. So how do I get it to be fit correctly on the screen? I hit the little button in the top left corner. Now to print it, this is supposed to look like a camera. Not a very good camera. I did not recognize it. I clicked that and it took a picture. How do I know? Well, because it showed it there. How do I see where the picture is? This button next to it brings up the gallery of the pictures I've taken. So as you're going through the lab, every time it says to print something, take the snapshot of it. It should show up over here. You can come here and you can click here to annotate, and you can give it a name like, Richard's Walk. And when it prints out, it'll have that with it, so you know, hey, that's what that one is. And so then when you're all done, after you've done all of the things and have all of the snapshots you want to print, then you click here on the print button. It prints the journal. That's what it calls this thing. Prints everything that's here. So if there are things here you don't want to print, well, you need to do something like only highlight the ones you want. Right now there's only one, so it's nothing to consider. Or delete the ones you don't want to print. When you hit print, they should print on the printer in room 123. You go over there, grab them, staple into your book, and you're done. All right. You have to answer some questions about your prediction. And notice you have now turn on the prediction data. And then you're going to each person in the group needs to try to match it. So what's that prediction data? Well, at this point, I'm going to assume I have everything else done. I have all my snapshots. And so I'm going to get rid of all the data here. How do I get rid of the data? On the bottom. I'm just going to delete all runs. And now it says to turn on the prediction with this thing that looks like the Google Drive triangle. So I click here on the down arrow that says prediction with no check mark. Click it. There it is with the check mark. So now I'm going to try to walk to match this. And I want you to do your best. When you have your best, then you'll once again take a snapshot of it, annotate it. Yeah. So I have it there so I can print it when I'm done. So I'll do mine. After I do mine and I have the snapshot here, then I'll go ahead and delete it and let my partner do it. Or if I'm really worried, I can just hide it from the graph. I'm not going to worry about that right now. Then we go on to part 2. I'm going to stay here for part 2. Part 2 means click on the tab for part 2. Shocking. What's different about this graph? It's velocity versus time. You're doing all the same things, but now with velocity versus time. And that's the end of the lab. Any questions? What was that? No, you all have a computer. Well, there's a computer at the front desk, and the detectors and stuff are in the cupboards.